Next, we'll discuss comparative statistics. So in comparative statistics, we're attempting to look at various distributions of different populations and compare them. This is what we do when we do hypothesis testing. Now this can be confusing because in statistics we can never really prove that anything works. Most of the time is spent attempting to disprove what's known as the null hypothesis. That is, what we try to do is to disprove that something doesn't work. This can be confusing, but it helps to look through some examples. So hypothesis testing. So here's the problem. Let's say you have two distributions of 21 people each. In distribution A, the average height is 67 inches with a standard deviation of 1.6. And in population B, the average height is 70 inches with a standard deviation of 2.0. The frequency histograms of these two populations is shown at the bottom of the slide. So what would your assessment be? Do you think that these populations have a different mean value? It looks as if they do, but perhaps this is just random variation. There's only 21 people who have been sampled in each of these two populations. That's a relatively small number compared to the total number of people out there that might be sampled for this type of question. So how do we test the hypothesis that these two distributions these two samples, come from two distinct distributions? So to reframe the problem in a more verbal format, the question is, are the people in group B taller on average than the people in group A? Or is the difference in heights just due to random chance? Well, we can frame these into hypotheses. So the null hypothesis, or often called H0, you can think of this as the opposite of what you're trying to prove. In this case, that group B is not taller than group A. The alternative hypothesis, or H1, is that group B is taller on average than group A. Comparative statistical tests are designed to help us accept one of these two hypotheses and to reject the other. But in reality, it's all about the null hypothesis and our attempt to disprove the null hypothesis. So, statistically speaking, there are two possible outcomes. One is that we can reject the null hypothesis. We would say that group B is on average taller than group A. Or we won't reject the null hypothesis. We can't technically say that we accept the null hypothesis. All we can say is that we don't reject it. In legal terms, this would be equivalent to saying somebody is not guilty versus saying that there's not enough evidence to convict. If you're ready for more, we'll move on. If the null hypothesis is mistakenly rejected, i.e., you conclude that group B is on average taller when in fact it isn't, you've committed what's called a type 1 error. The probability of making a type 1 error is called alpha, or the p-value, and this is often the output of statistical tests. Now, traditionally, we define a p-value, a critical p-value, as being less than 0.05, and at that point, we would reject the null hypothesis. This means we think that it is either 5% or less likely that we have committed a type 1 error. That is, we have concluded that the null hypothesis is incorrect when in fact it is correct. In contrast, a type 2 error is if the null hypothesis is not rejected, but a statistically significant difference does in fact exist. The probability of making a type 2 error is called beta. And it's important to remember that the p-value itself has nothing to do with a type 2 error. So one question is, which would be worse for you to make, a type 1 or a type 2 error? Often we are making trade-offs when we think about a diagnostic test between the probability of making a type 1 error or the probability of making a type 2 error. For example, suppose you've been given a new drug by a pharmaceutical company touted as, quote, a new cure for diabetes. The company claims that their research shows patients who use this medicine become disease-free within 6 months, but it may cause serious side effects in a small number of people. If the company mistakenly rejected the null hypothesis, what does this mean for your patients? Well, remember, the first rule in medicine is to do no harm. So perhaps it would be better to err on the side of a type 2 error and to later be proven wrong than to err on the side of type 1 and potentially inflict harm with no evidence of benefit. These types of trade-offs are commonly made when deciding what the threshold value should be for deciding whether or not a diagnostic test is positive or negative, and we'll discuss this further in subsequent lessons. How can we be sure that we can overcome a type 2 error? In other words, what might cause us to believe that we cannot reject the null hypothesis? Most commonly, this is because we didn't have a large enough sample size. Think of it this way. Which is more convincing? If you had negative results from a 100 patient trial or negative results from a 10,000 patient trial? The greater the number of subjects or patients in a clinical trial, the greater power you have of detecting a difference between a treatment group and a non-treatment group. So a type 2 error is going to be very much dependent on this sample size in a population. Typically in clinical trials speak, we refer to the power of a study to detect a change, and power is also can be computed as 1 minus beta. It is related to the sample size and is the measure of an ability of a study to detect a true difference. The larger the sample size, the greater the power, and the greater the power, the more accurate the study. Most commonly, we demand that clinical trials have a power of 0.8 or 80%. That is, that the trial is 80% likely to detect a real difference between a treatment group and a non-treatment group if one exists. Practice question. In a recent study, researchers showed that bathing infants more than 4 times per week resulted in a greater number of candidal infections than babies that were bathed 3 times per week. The p-value for the two groups studied was less than 0.001, and the power was 82%. What is the chance that this group made a type 2 error? So recall, type 2 error is the likelihood of missing a significant difference when one actually existed. And the type 2 error has nothing to do with the p-value that was generated by comparing these two groups. The type 2 error is actually predetermined before the study even began. It's based almost entirely on the sample size and the expected noise in the outcome measure. So in this case, the power was predetermined. It has nothing to do with the p-value of 0.001 that's shown in this question. It has everything to do with the 82% that's shown there. So the power of this study was 82% to detect a difference. That means that there was an 18% chance that there was a significant difference that was not detected by this study. And for that reason, the correct answer here is 18. Power is 1 minus beta. Hypothesis testing. We can describe several scenarios where we compare the true situation, that is, what is the reality in terms of two different groups that we're studying, versus what we concluded from our hypothesis test. So for example, if in the true situation there really was a difference between the two groups that were being studied, and we found that a difference existed, that is, we rejected the null hypothesis, this is reflected in the power of the study, that is 1 minus beta. However, there are two other scenarios where errors could be made. So for example, if in the true situation there was no difference between two populations, but we inappropriately rejected the null hypothesis, that would be reflected in our type 1 error, which is quantified as alpha. And then finally, if a true difference existed between two populations, but we were unable to detect that difference, that would be reflected in the type 2 error, which is quantified as beta. So in hypothesis testing, the bottom line is that to compare groups, you first perform an appropriate statistical test. The output of the test is P. This is the probability of mistakenly rejecting the null hypothesis. We then compare P to alpha. Alpha is most commonly set at 0.05. If P is greater than alpha, in this case 0.05, then H naught should be accepted. That is, we are accepting the null hypothesis that there is no difference between two groups. If P is less than alpha, again here it's 0.05, then H naught, or the null hypothesis, should be rejected. That is, we conclude that there is a real difference between the two groups. Practice question. A group of researchers mistakenly conclude from a poorly designed experiment that acetaminophen cures the common cold. They have committed which of the following errors? Alpha error, beta error, type 1 error, or type 2 error? What have they really done? They've mistakenly concluded that a difference exists between two groups when no difference existed. This we commonly call type 1 error. There's no such thing as alpha error or beta error. Alpha and beta are simply parameters by which we determine how much error we're willing to accept. We set alpha, typically at 0.05. We set beta, typically at 0.2. But these terms, alpha error and beta error, do not exist. So the correct answer here is C, type 1 error. That concludes our discussion of comparative statistics.